In this video, we're going to further unpack the idea of disjoint cycle notation, which we introduced in the video called Notation for Permutations. So here I've written the array notation for a certain permutation, which I'll call sigma. And sigma is an element of S8 because it is a permutation of 8 numbers. All right, so we're going to write down disjoint cycle notation for sigma. So we have sigma equals, I'm going to follow the same algorithm I used in the previous video, where I just start at 1. That is, I start with the least unused number. And I start tracking what 1 does if I apply sigma. So I start by going from 1 to 3. Sigma takes 1 to 3. So I put that number next in my cycle notation. And then I see what 3 goes to under sigma. Well, sigma sends 3 to 5. So next I have a 5. And then sigma sends 5 to 2. So then I put a 2. And then sigma sends 2 to 8. Okay, this is turning into kind of a long cycle here. But then I see that 8 goes back to 1. Sigma sends 8 to 1. So that's the end of my cycle. And then I just inspect this and say, okay, I have a 1 and a 2 and a 3 here, but I don't have a 4. So since 4 is the least unused number, I'm going to start there for my next cycle, and then look over here at my array and I say, oh, well, 4 goes to itself. So that's the end of that cycle. That's just a 1 cycle. By the way, this is called a 5 cycle. This is a 1 cycle. I could just hyphenate the length of the cycle to the word cycle, and that's a way of describing how long each cycle is. Okay, anyway, finally, I have 1, 2, 3, 4, 5, but I don't have 6 or 7. So I'm going to start a new cycle with 6. And note that that goes to 7, and 7 goes back to 6. So that's the end of that cycle. So as always, I just continue each cycle until I run into a number that comes back to the one that I started the cycle with. So if I get to 8 and sigma sends 8 to 1, that's the end of my cycle. And I can represent that pictorially like this. So this particular permutation, sigma, acts on the elements of the set 1 through 8 in a few different clusters. So this cluster, everything goes cyclically like this. And then 4 goes to itself. And then 6 goes to 7. 7 goes back to 6. So if I wanted to visualize what sigma does, this might not be such a bad way to do it. This shows me a picture of what each element of the set 1 through 8 goes to. But here I have a nice compact notation that doesn't require drawing any pictures. It just requires writing down a few cycles. And then once I have those cycles, anyone who understands cycle notation can look at this and say, oh, I know what 6 goes to. I know what 5 goes to. Now, one thing you'll notice about the cycle notation is if I just followed my algorithm was start a cycle with the least unused number, starting with 1, and then here I used 4 because 4 was the least thing I hadn't used. And then here I use 6 because that was the least thing I hadn't used. If I just follow that algorithm systematically, I get 3 cycles, all of which are disjoint. Disjoint means that they have no numbers in common among them. All cycles are disjoint, which is why we call this disjoint cycle notation. But here's a question, and maybe it seems like a silly question because now we've done a few examples and it's always come out like this, but the question is, why does every permutation seem to have a disjoint cycle notation? And in fact, does every permutation have a disjoint cycle notation? Like, is this really possible for every permutation in Sn? And I claim the answer is yes, and we're going to prove it in this video. So we're going to prove that every sigma in S sub n, there we go, can be expressed as a product of disjoint cycles. So that every element of this set, the set 1 through n, appears exactly once. So here's the proof. So first we're just going to write down how we do it, and then we'll prove that nothing goes wrong. The main thing that it seems could go wrong is, well, maybe I start another cycle, like maybe I'm in a larger set than 8, and I start another cycle with 6, and then somewhere along the way here, I run into a number that's already been used in a previous cycle. Now, I claim that that's actually not going to happen, but there's some mathematics, important mathematics behind why that never happens. So let's just see if we can start writing a proof here. I'm going to use a different color for this. All right, so I'm going to start by just writing down the algorithm for finding this disjoint cycle notation. So let's let n be a positive integer, and let's let sigma be an element of S sub n. All right, so we have a sigma. We know what sigma sends everything to, although we're not writing in this proof because we're trying to write a general argument here. But we're going to say we'll produce, or we'll express, let's say express, sigma as a product of cycles as follows. All right, so let's let A11 be the least integer in the set 1 through n, which, okay, look, there's no trickery going on here. I know what that is, but I'm just trying to write this in a way that's going to be consistent with what I write later. So I know that that least integer is 1. There's nothing subtle here. It's just we're writing this in a way that'll generalize a bit. Okay, so that's, in fact, I'll write here. That's 1. All right, so let A11 be that integer. And then, for each j, given a sub 1 j, define a sub 1 j plus 1 to be sigma of a sub 1 j. All right, so let's say for each j greater than or equal to 1. There we go. Given a sub 1 j, define a sub 1 j plus 1 to be sigma of a sub 1 j. So what I'm saying here is I'm going to build a cycle A1, A11, A12, A13, up to, and then whatever I end at. But we need to talk about why this cycle actually ends. So we're going to continue this process until an element repeats. As it must eventually, okay, well, why must we eventually repeat something? Well, that's because the set that we're pulling from here is finite. We can't go on forever and never have a repeat. All right, so this process will eventually repeat an element, and when it does, let the last element before the repeat element before the repeat be a sub 1, and then what do we call this? Let's call this k1. Okay, so for each n, k sub n is going to represent the nth cycle length. So k sub 1 represents the first cycle length. All right, so I'm going to build a cycle, and I'm going to stop here. And now I claim that a sub 1 k1 plus 1 is 1. In other words, the first repeated element is 1. Okay, why is this true? Why is it that the first repeated element has to be 1? Well, if it isn't 1, then it's one of these other numbers here. This one, or this one, or this one, or maybe even this one. Okay, and I claim that can't happen. Suppose by way of contradiction, and I always abbreviate by way of contradiction BWOC. Suppose by way of contradiction, the first repeat is a sub 1 j for some j greater than 1. All right. Well, in that case, what do we know? Then we know that sigma of a1 j minus 1 is a sub j, and also sigma of a1 k1 is j, because that's the number that gets sent to, or is a sub j, because this is the first number. This is the number that we said gets sent to the first repeat. Okay, so if that repeat is a sub j, then we've got two different numbers here, and I claim that they have to be different, getting sent to the same number. But a1 j minus 1 is not equal to a1 k1 because we assumed there were no repeats prior to k1 plus 1. Okay, this is a contradiction because, well, I have two different numbers here, both getting sent to a sub j by sigma, but sigma's 1 to 1. It's a 1 to 1 function. It's a bijection. Okay, so we have a contradiction. Therefore, a1 k1 plus 1 has to be equal to 1. The first element that gets repeated in our cycle has to be 1. Okay, now I realize that the way I've written this part of the argument is really notation heavy, so I want to come back and see if I can tie it to this example here, just the essential reasoning that we did here, because I feel like having that out in the ether is not advantageous. All right, so let's look back at our sigma here. So we were looking at sigma for this permutation here, this array notation, and we were trying to write sigma as a product of cycles. Now, as we got started, we said, oh, 1 goes to 3, 3 goes to 5, 5 goes to 2, and then 2 goes to 8, and then 8 goes back to 1. Now let's just suppose, for the sake of argument, that 8 had gone to something else, like 5, that was already in this cycle. Now I know that in this array notation it very clearly does not, but we're trying to assume a counterfactual just to make an argument here. Well, if 8 had gone to something else like 5, then we've got a major problem here, because 3 already goes to 5. We can't have something else like 8 also going to 5. That would violate sigma being 1 to 1. So that's the idea that's getting captured in this very notation-heavy way in this argument here. And I think there could be a debate about whether this notation really helps understanding of the argument or not, but it is necessary for making it general. And actually, as I look at this, one thing I'm realizing is I didn't make this quite generalizable enough because, well, I said, okay, so I claimed that this first repeated element is 1. It will be 1 for this first cycle because we're starting with 1, but in general, it'll be something more like this. I should call it a sub 1, 1, the first element listed in the cycle. And then same here, this should be a sub 1, 1. A sub 1, 1 was 1, but it won't look quite like that in other cycles. Okay, so now how does the argument proceed from here? So at least I've shown that the first cycle has to be something reasonable, where we start with an element like 1, and then the first repeated element is also 1. So what next? Let's come up here. I'm going to zoom in a bit. There we go. Okay, so now that we've created the first cycle, which we're calling A11, A12, and so on up to A1, K1. And by the way, the reason I'm using two subscripts at the same time here is the next cycle is going to be called A21. So there's really two subscripts. The first one tells us which cycle we're in, and then the second one represents position within that cycle. Okay, so now let's change colors a bit. So next, to create the second cycle, or the next cycle, let's just say the next cycle, because I don't want to have to rewrite this argument every time we create a new cycle. So to create the next cycle, once the nth cycle has already been created, or I'll say has just been created, well, first let's look at whether there's anything left. If there's nothing left, then there's no next cycle to create. Is every element of this set, 1 through n, in a cycle? If so, then we are done. And I claim that we're done because if we know that every element of 1 through n is in a cycle, then that's going to tell us what each element of this set gets mapped to by sigma. Like if I look at, say, 17 in here, and I want to know what 17 goes to, well, I can find a cycle that contains 17, and that cycle will tell me what 17 gets mapped to. So in that case, we know what every element of this set maps to. So in that case, we're done. If not, let's let A sub m plus 1, so new cycle now, 1, be the smallest element or least element remaining. All right, so we're going to start our cycle with that, and then use the same process as before. to create the m+1th cycle. So the same process I described over there. Sorry, my pen's skipping again. Okay, so once I have all of this in place, I have an algorithm, and it's a perfectly sensible algorithm for writing a permutation as a product of cycles. What I don't know yet is why all of these cycles have to be disjoint. That's the thing that I have to prove now. So I think I'll switch colors again. I'm just going to switch to a darker green. I'm in a very green mood today. There we go. And let's go really dark. There we go. All right, so why are all the resulting cycles disjoint? Why are all the resulting cycles disjoint? Well, let's suppose, again by way of contradiction, that some element lives in more than one cycle. I guess lives in is not technically mathematical terminology, but I think it expresses the necessary idea pretty clearly. More than one cycle. And we're going to express it mathematically in just a moment anyway. So what I want to do here is I want to pick out the first such instance. So let's say A sub M, and then we'll call it J for Michael Jordan, just kidding. And A sub M prime, J prime be chosen. And then I'm going to give a bunch of conditions on how they're going to be chosen. Chosen so that, okay, first of all, I want to choose them so that these are elements of two distinct cycles that are the same element. So number one, A sub mj equals A sub m prime, j prime. In other words, I want to capture the idea that there is some repeat between two different cycles. Okay, so that first of all. Number two, m is less than m prime. So in other words, these really do come from two different cycles. And m is chosen to be as small as possible, subject to prior conditions. In other words, I need these elements to be duplicates of each other, but given that, I want m to be as small as possible. In other words, I want to try and find a duplicate in a cycle that is as early in my sequence as possible. And finally, subject to all of that, I'm going to ask J prime to also be as small as possible. As small as possible. I'm not going to ask for the same thing about J, and I'm not going to ask for J and J prime to be different, because they might not have to be. It may just be that the third element of cycle number 2 is the same as the third element of cycle number 8, and that is perfectly fine. I'm just going to ask for us to find an element in the m prime cycle that is as early as possible in that cycle that's a repeat. So in other words, I'm going to stop just the moment that I see a repeat. And now from all of this, I'm going to try and get a contradiction. And before I jump into writing more of the proof, I'm just going to let you in on what the idea is going to be. Here's the idea. If I have a repeat, then each of those elements in one cycle and in the other cycle, in the mth cycle and the m prime cycle, each of those has to have a preimage. Because sigma is 1 to 1, those preimages have to be the same, which means there's going to be another repeat there. There has to be. So here's the argument. Here's the way it plays out. So we know, since sigma is 1 to 1, the preimages of AMJ in cycle M and A m prime j prime in cycle m prime must be the same. In other words, sigma cannot send two different elements to these two guys, which are the same. So the preimages of those must be the same element. Okay, so this means one of two things. Either, first of all, j prime equals 1. Well, that's not going to happen. If j prime is 1, that means that what I'm talking about here is the first element of a cycle, but I wouldn't make it the first element of a cycle if I'd already used it. Remember, my algorithm said, let the first element of each cycle be the least thing that hasn't been used yet. So this is a contradiction. Since I would never put, or really my algorithm would never put, a repeat at the beginning of a cycle. Which means that my j prime must be greater than 1. But that also is going to create a problem. Because then I know that a sub m prime j prime minus 1, that is the element before this dude here, must be the same as the element of cycle m that gets sent to a sub mj. And I'm being purposefully a little bit coy there, because it's possible that that's a sub mj minus 1, or it's also possible that j could be 1, which means the element that gets sent to a sub m1 is actually the one at the end of that cycle. So I'm purposefully not writing down what the subscripts have to be, but I know that there's an element of that cycle that gets sent to this. There has to be somewhere. So that means that there's a repeat earlier than a sub m prime j prime in cycle m, or cycle m prime. Namely this one. That also has to be a repeated element. That's a contradiction. So the only conclusion we can reach here logically is that there can't be any repeats at all. So there can't be any duplicates between different cycles. And at this point we're done, because we've written the entire permutation sigma as a product of cycles. Every element is involved somewhere, even if it's in just a one cycle. And finally, there are no duplicates between different cycles. So let's zoom out. Let's just sort of cast our eyes on this entire beautiful process again. Oh, look at that. The two columns of this ended up being exactly the same length. Definitely not planned. But anyway, that's it. So this was probably not the most entertaining proof that we've done. I feel like, at least in my experience, proofs of algorithms always end up being kind of technical and even a little bit tedious after a while. But I just wanted to illustrate what the mathematics is of showing that this algorithm always works, that it always produces disjoint cycles. And I hope that one thing you realize now is that it's not trivial. The mathematics I was expressing here, even though it captured ideas that are pretty simple, the ideas did use real mathematics. They used the fact several times that sigma is 1 to 1. And that's something that we hadn't used in just talking about the algorithm. So I hope this illustrates that the proof really does give us something that just talking about the process as though we imagine it always works doesn't.